Let's look at a famous example of iteration. We're going to study the Fibonacci sequence. That's Fibonacci, a mathematician from long ago. And here is his sequence. It starts with 0, and then 1, and then every element after that is the sum of the previous two elements. So 0 and 1 make 1, 1 and 1 make 2, 1 and 2 make 3, etc. And you can see that it starts getting fairly large before too long. Now, Fibonacci did not invent this sequence. It was discussed and described by mathematicians long before him, but he made it popular in the West, and so we still refer to him every time we see this sequence of numbers. Every Fibonacci number is associated with its index, the position in the Fibonacci sequence. So we usually call this the 0th Fibonacci number, the 1st, the 2nd, the 3rd, the 4th, and the 5th, etc. So the 5th Fibonacci number is 5. Now it might appear in position 6 in this sequence, but we call this one the 0th Fibonacci number since it's 0. That's just a convention. Now, who cares about the Fibonacci sequence? Well, it certainly has interesting properties. You can make what's called the golden spiral by tiling together squares whose side lengths are Fibonacci numbers. So here's a square of side 1, 1, 2, 3, 5, 8, 13, 21, 34, etc. And then if you draw a spiral going through the intersection points of these squares, you get an ever-expanding spiral that looks particularly well-balanced to the human eye. It's also a spiral that people like to look for in nature. Here is a cabbage, where somebody thinks they've discovered the golden spiral. Okay, enough about the Fibonacci sequence. Let's figure out how to compute it using a while statement. Here's a function that takes n, the position or index in the Fibonacci sequence, where we want that Fibonacci number, and it computes the nth Fibonacci number for n greater than or equal to 1. It does that by keeping track of various values and then executing a while statement. So when you're designing an iterative function, one of the most important things to think about is what information you need to keep track of in order to perform the iteration. In this case, in order to compute that the next Fibonacci number is the sum of the previous and the current one, we need to keep track of what those Fibonacci numbers are. So we start out at the beginning of the sequence. The 0th and 1st Fibonacci numbers are 0 and 1. And then we also need to keep track of where we are in the sequence. So that's how we use k here. K keeps track of the index, and throughout the execution of this while statement, k will be telling us what Fibonacci number is bound to the name cur for current. Now the current Fibonacci number at the moment is the first one, this one, 0th 1st. But as we execute this while statement, k will change and cur will change, and k will tell us which Fibonacci number is cur. Okay, this says k less than n. We're going to rebind pred and cur to be the next numbers in the sequence. So the predecessor is bound to the current one, and a new current value is computed. And here we use the definition of the Fibonacci sequence. The next Fibonacci number is the sum of the current one and its predecessor. And we bind that to be the new current Fibonacci number, which has an index 1 larger than before, so that's why we bind k to be k plus 1. Now the structure of the while statement allows us to perform this computation many times until we've found the nth Fibonacci number. So we keep doing it until k is less than n, and that means at the end, k equals n, because we're just adding 1 to k each time. So we've found the nth Fibonacci number, we've bound it to cur, and we return it. In the environment diagram for this example, we're keeping track of the names pred, cur, n, and k in a local frame for calling the fib function. n never changes. So if we're trying to find the fifth Fibonacci number, which is 5, then n would be 5 at the beginning, pred and cur would be 0 and 1, and k would be 1. Now we'll track which values are bound to these names every time we finish executing k equals k plus 1. So the first time through, we'll rebind pred and cur to be the next two numbers in the sequence, and say now cur points to the kth Fibonacci number, where that is the second Fibonacci number. There it is. And then we execute the body of the while statement again, marching pred and cur up the sequence and changing k at the same time. We're going to do that 4 times. Now k equals n, so it's not the case that k is less than n. We're finished executing the while statement, and we return cur, which is the fifth Fibonacci number, 5. Here's a discussion question. What if, in the body of fib, I had made the following change? I had bound pred and cur to 1 and 0, and k equals 0. Is this alternative definition of fib the same or different from the original one? Pause the video and think about that for a moment. Then we'll discuss together. So this is still a correct implementation of fib for every n greater than or equal to 1, just like our old definition. But it's even better because it can compute the 0th Fibonacci number correctly. So we found a particular input value where this does a better job than the old one. So in particular, if n is 0, then cur is 0, which is the 0th Fibonacci number. By the time we reach the while statement, k will be 0, n will be 0, and so the body will never be executed and will return 0, which is the 0th Fibonacci number. Excellent. Our old version didn't do that. But what about with n equals 5? Well, we start out with cur 0, and then we're actually going to execute the body of the while statement 5 times instead of 4, because we started with k equals 0 instead of k equals 1. So cur will be 0, and then 1, 1, 2, 3, 5 will still get the fifth Fibonacci number.